All right, this is our lesson for finding roots of polynomials. Um, I'm starting with actually this quadratic and reviewing that we have a factoring method which can easily get us from standard form to factored form, which is great because from factored form we can get our roots. This is why we spend so much time talking about factoring, because it's an easy way to find the solutions. Well, this lesson today is for what if I don't have a trinomial quadratic, or I have something longer that doesn't have factoring methods? How can I get it into a factored form so that I can use those factors to find the roots? And what we have to help us out with that is something called the rational zeros theorem. This is great for when we don't already have a known factor or zero for a polynomial. And it says that all of the rational zeros, so rational is a word that we use for things that can be fractions, and zeros means the zeros of our polynomial, the roots, the solutions. This theorem allows us to take a polynomial and create a bank of potential zeros that we can check out one at a time to see if they satisfy our polynomial. And so on the front of this page, we're going to be using this theorem and just practicing the skill. And then on the back of the sheet, we will apply the skill to an actual problem and show how it can be helpful. So the way we begin is we take the factors of the constant term, which is always the last term when you're in standard form, and the factors of the leading coefficient, which is always the first coefficient when you're in standard form. We find the factors of each of those numbers and we create all the possible fractions we can out of those two sets of numbers. So here's how that would look. So starting with this first example, the constant at the end is going to be my p. So we're going to be writing them in this form. So this is p, and the leading coefficient is going to be my q. And we're going to take all the factors of the p matched up with all the factors of the q and get all the possible combination fractions that we can. So the leading coefficient was 8, and the constant term is 3. So the factors of the constant term p are 1 and 3, but not just 1 and 3, the positive and negative versions of it, because positive 1 times positive 3 gives me positive 3, but negative 1 times negative 3 also gives me that. So I really have 4 total factors here. And then the factors of the leading coefficient, so the 8 are 1, 2, 4, and 8, right? Because 1 times 8 will give me 8, 2 times 4 will give me 8, and the negative versions multiplied also will give me positive 8. So now that I have my factors of the p, or constant, and factors of the q, or the leading coefficient, we're going to create all the combinations p over q that we can come up with. So I like to take the first factor for my p and match it up one at a time with all the factors of the q. So I'll have 1 over 1, which is 1, 1 over 2, so I'm matching this here, 1 over 2, 1 over 4, and 1 over 8. So there are 4 potential zeros for my polynomial. And now I'm going to do the same thing using the 3 as a numerator matched up with all these as denominators. So 3 over 1, which is just 3, 3 over 2, 3 over 4, and 3 over 8. Now these are not all the zeros of my polynomial because I have the positive version of them and the negative. So I really have 1, 2, 3, 4, 5, 6, 7, 8, 16 total solutions represented here. My polynomial only has 4 solutions. Whatever the degree is, that's how many zeros you have. So I only have 4. So it's got to be 4 of these, not all of them. And we if we're not doing it in this problem, but we could test them out one at a time, which I'll explain here in a minute how to do that. But we could test them out one at a time, and wherever they do end up being would have to be out of this pool of potential zeros. So here's some basic steps that we're going to follow. One is to find all combos of P over Q. Anytime you get a fraction, you want to simplify it. So simplify fractions. And then the third thing is don't repeat numbers. So if you end up having, in two of the combinations, end up giving you the same number, don't write it down a second time. Okay, let's look about how to do that in this one. This one's got a little more factors, so it'll be a little longer. My leading coefficient is 10. These are my Q's. My constant term is 12, that's P. So all the factors of the constant, I'm just going to make a little table of everything. It can be 1 and 12, 2 and 6, or 3 and 4. So it's the positive and negative versions. And then all the factors of 10 are 1, 2, 5, and 10. So we just get started. I like to start with the P over every single Q. So that's going to give me 1 over 1, which is 1, 1 over 2, 1 over 5, and 1 over 10. So then I'm going to switch to this 2 as my numerator. 2 over 1 is 2. 2 over 2, so 2 over 2 simplifies to 1, which I already have, so I don't need to write that again. And then I have 2 over 5. And then I have 2 over 10, so this 2 over this 10, which simplifies to 1/5, and I already have that here. So I'm not going to write it again. So I want you to pause your video and finish out the rest of those, and then come back and compare yours with mine. All right, here are all of mine. Check yours with mine, and then correct any mistakes you might have. All right, so all we did here was practice the skill. So on the back, we're going to apply it so you can see why we have it. So this is one big problem back here. We're given a function. We want to find the y-intercept, the roots, and then we want to graph it using our information from some previous lessons. So find the roots of the following function, write it in factored form, identify the y-intercept, sketch a graph, and it gives us the starting information. One factor is x plus 2. So this is a given factor. So when I start factoring in a minute, I'm going to start here. But let's go ahead and do our y-intercept. Remember, that is when x equals 0, because wherever the graph crosses the y-axis for the y-intercept, x equals 0. So algebraically, we just plug it in. So if I put a 0 for all these x's, those terms all drop off, leaving me positive 8. So there's my y-intercept. And then it says to use synthetic division using the given factor or root. So we got lucky that we were given a factor. Let's pretend for a minute that I wasn't. If I wasn't given a factor, I would do my p's over q's. I'd have a whole set of numbers, and I would start testing them one at a time. But since I'm given a factor, I am going to use synthetic division to start factoring. And remember, if you know something is already factored, for example, I know that for 8, 2 is a factor. So if I do 8 over 2, That's going to give me 4, and that has no remainder because I know it goes in evenly because it's a factor. So the same thing is true for polynomials. If I already know this is a factor and I do division with it, divide by x plus 2, I should have no remainder. So with my synthetic division, remember that last number is your remainder, we should be getting a 0. So here we go with our synthetic division. And sure enough, I have a remainder of 0. And again, the point of the rational roots theorem was pretend you weren't given x plus 2 as a factor. You would find all your p's over q's, and you would use synthetic division and test them right here. Like if one of your p over q's was 3, you would test 3, look for a remainder of 0. If you didn't get a remainder of 0, it's not a root. And so you would trash that option and you go to the next number and the next until you find some that give you a remainder of 0. But luckily, this problem gave us one. So now if I add my x's back in, I start with 1 degree less, so 6x squared minus 11x plus 4. So these are my coefficients. And now that I have a trinomial, now I can use my factoring method. What multiplies to AC and adds to B, negative 8 and negative 3, divide by the A value. This is negative 1/2. This is negative 4/3. I go and write this in my factored form. Now, this isn't my finished factored form, but what's great about it is I can already see my roots. From the first factor, x is 4/3, and from the second factor, x is 1/2. But we do want to swing this up for our proper factored form. So my final factored form is 3x minus 4 times 2x minus 1 times the original factor that the problem gave me, x plus 2. My roots from each of those factors are 4/3, 0, 1/2, 0, and negative 2, 0. So I'm going to go ahead and graph my points. I've got a y-intercept at 8. This is not going to be drawn to scale. I have roots at negative 2, 0. 4/3 is 1 1/3. And then 1/2, 0. Because each of these factors have a multiple of 1, we know that the behavior at each of these roots is it crosses straight through. There's no bounce, there's no hang. Because we have standard form, we also have some more information. Our degree of 3, which is odd, tells me that the end behavior is opposite. So it has opposite ends. My positive A value of 6 tells me that the graph is going to be up on the right. So if I'm going up on the right, that means through this root I'm going up. Down on the left means down here. There's no bounces or hangs. We're just going to estimate where it turns around. I'm going to go through my y-intercept and then come down here. We don't exactly know where it's going to turn here or here. We could substitute in an x and find it, but right now we're just sketching.